Hey, welcome back. This is Calc 1, now in Chapter 4. And the beginning of Chapter 4 will have some really high-powered theorems from calculus. The first theorem is the extreme value theorem, which says that if a function is continuous on a closed interval, then f has both a max and a min on the interval. Okay, and the book's going to give you some figures, some pictures to kind of help you figure that out, help you understand what's going on there. Okay, so the first picture, 3, 4, is that of a function which is continuous on a closed interval. Okay, so it goes like this somehow, and it jumps back up to here. And you'll notice it has both a max and a min. When I talk about maxes and mins, I talk about the y values. I'm not talking about the location of the max and min, the x values. Okay, so the heights, the y values, are where we talk about the maximum. So this has a minimum value of 1, and that occurs at x equals 0. So min of 1. And then it has a maximum value at this endpoint. At x equals 2, it goes all the way up to 4. Okay. So that's guaranteed to happen if you have a continuous function on a closed interval. So looking at other cases then, so this case, it's continuous but only on this like open interval. Okay, so just kind of the same kind of graph. Oops, oh, great. Okay, so yeah, here. Okay, so it's not that it absolutely won't have a min or a max. No, it's just you need to have continuity on a closed interval for it to be guaranteed to have a min and max. You can think up examples that will have mins and maxes, but it won't be necessarily continuous on the closed interval, right? So, for example, this picture is not it's not continuous on the closed interval, but it certainly has a min and a max, right? Maybe it goes up to 3 and then jumps back down to maybe 0 right here, right? So certainly on the interval from -1 to 2, it's not continuous. It has these open these holes at the endpoints, but it will achieve a max and a min. Its min is at 1. Its min is at 0, and it has a min of 1, and then its max is at 1, and it has a max of 3. Looks like 3. Okay, so this one does have a min and a max, but the deal is not all functions, if they don't meet this criteria, will have a min and a max. For example, the second picture does not have a max. Okay, so it has a min, again, of 1, which occurs at 0, but it doesn't have a max. Okay, so if you look at all the y values, especially going towards x equals 2, you can never find one that kind of is the maximum, right? You could say, well, there's 3.9 at 1.9 comma at x equals 1.9, you'll have y values like 3.9. But then if you go 1.99, you'll have y values like 3.999, etc. And you can keep on pushing it, and there's no way to find a maximum y value, because as soon as you think you find one, you can just push the x value a little farther, and the corresponding y value will be a little higher. Okay, so it's kind of like there's no immediate predecessor to things and the real numbers. Okay, so what number is directly touching 0? It's that kind of question. And there isn't any. It doesn't seem like there is anything, because if you say one thing, then somebody else can find something that's a little closer, So anyways, no max. Let's look at another one. Okay, so this one, 2, 3, 4. So let's say it is kind of continuous, but then it has maybe a hole right here, and then it's redefined up here. So it has a limit inside this interval. Everything has a limit. Okay. The problem with this one, it has a max, certainly, 1, 2, 3, 4, which occurs at x equals 2. But it doesn't have a min. And again, as you could press closer and closer to 0, like 0.1, the corresponding y value will be like 1.1. At 0.001, the corresponding y value is a little smaller. It'll be like 1.001. And you could keep playing that game forever and ever. So in this case, there's no min. Okay, so if you have a closed interval, though, and the function is continuous, you will have a max and a min. Okay, so I think we kind of beat that to death. Relative extrema. Okay, we're in the business of finding these relative extrema. We want, so you may have a picture where there are multiple kind of extrema for different intervals, right? So if you have a picture like this, obviously there's kind of a global extrema, and maybe they have a name for that in the book. I don't remember. What is it? Absolute maximum, right? For the entire graph, that absolute max looks like it's up here, right? But there's local kind of extrema. If you just look in the interval from here to here, there's kind of a relative extrema right here. Relative to this interval, this is the highest value, you know. So we want to identify all of those kind of values. We want this guy, we want this guy, we want this guy, et cetera, et cetera. That's the name of the game. That's what we want to do. So the book will kind of begin you with some examples of, and how we're going to do it is through the derivative. Okay, so they're going to give you some examples like f of x equals 9 times x squared minus 3 all over x cubed. And if you graph it, it looks like the following picture. Okay, and it kind of goes like that. So it has this relative extrema, this maximum sitting right here. Okay, and basically, again, we're going to be looking at the derivative. Okay, and we want to evaluate the derivative at that point. The book is suggesting that we take on this adventure. Okay, so first we need the derivative, and I'm going to have to do some low d high minus high d low baloney. All right, so let me rewrite this as 9x squared minus 27 all over x cubed. Okay, so low x cubed d high 18x minus high 9x squared minus 27 d low 3x squared all over the low squared. So that'll equal 18x to the 4th minus 27x to the 4th plus 81x squared all over x to the 6th. 18 minus 27 looks like negative 9x to the 4th plus 81x squared all over x to the 6th. And we want to evaluate the derivative at this maximum value. So it occurs at x equals 3. Okay, we want to see what happens to the derivative. All right, so if I plug in 3, I'll get what? Negative 9 times 3 times 3 is 9, so 81 plus 81 times 9 all over 3 to the 6, whatever that is. The numerator is additive opposites, right? Negative 9 times 81 plus positive 9 times 81 is 0. So we're going to end up with 0. And it turns out that's going to be a characteristic we look for. We want to know where the derivative is equal to 0 because it turns out those are the places, or at least those are some of the places that maximums can occur. Okay? Okay, and I say it's some of the places because there are other possibilities. In particular, if we look at another example, and here we'll look at the absolute value function, right? This thing clearly has a minimum at 0. Okay? So here it has a min. Okay, but it's not differentiable there. If you don't believe me, you can go ahead to the, and we're going to look at the two different directional derivatives here. The limit as x comes in from the left, using the alternate version of the definition of the derivative, f of x minus f of 0 all over x minus 0. And so that will be the limit as x goes to 0 from the left. X, absolute value of x is negative x if x is less than 0, and then x if x is greater than or equal to 0. So I'm going to replace f of x with negative x because the x values I'm looking at are coming in from the left. Right? So on the graph there, I'm coming in this direction. In other words, all my x values are negative. In other words, f of x is equal to negative x in that setting. And then I plug 0 into the function, so that'll be minus 0 all over x minus 0. And of course that thing is just going to be negative x over x, which is the limit of negative 1, which will end up giving me negative 1 for the derivative at 0 coming in from the left. Okay, so the left-hand derivative, I guess they call it. The limit as x goes to 0 from the right, then I'm going to go do the same thing, right? So f of 0 over x minus 0, that is the limit as x goes to 0 from the right. This time I have to use x instead of negative x. It'll be x minus 0 again over x minus 0. That'll just be 1. Okay? And you see that the left-hand derivative and the right-hand derivative are different. So therefore, there's no derivative at 0, not differentiable at 0. And this turns out to be the other characteristic of relative maxes and mins. So there's kind of two possibilities. Either the derivative will be 0 or the derivative will not exist. Okay, okay, so we define those kind of points as critical numbers. Okay, so section 3, a lot of definitions. Critical numbers. And let's define it. So let f be defined at C if f prime of C is equal to 0, or if f is not differentiable at C, then we're going to say that's a critical number. Then C is a critical number. So first off, clearly the f has to be defined. If it has a min or a max, that's a number, right? That's going to be like it's 150 or 203, right? So f has to be defined. Also, just because it's a critical number, I don't think that necessarily implies that it has to be a min or a max. So clearly, if you have the cubic function or the cube root function, something like that, you're going to have a problem with the derivative at 0. It'll have like a vertical tangent right there, so it won't be differentiable right there. But clearly, that's neither a min or a max. Okay, so just identifying the critical numbers won't be enough for us. We can't say, "Ooh, there's a critical number, therefore it must be a max." No, you'll still have to do these tests, which we'll get in the next section. Okay, so anyways, one thing we can say is kind of the other direction. So a critical number does not necessarily imply a relative extrema, but a relative extrema does imply a critical number. So that's it used to be Theorem 4.2, so I'll call it that. If f has a relative max or min at x equals c, then c is a critical number. Okay, okay, we want to prove this. So we're supposing that somebody has determined that there is a relative max or min at this x value. And then we're looking at the derivative in order to see if it turns out that it's a critical number. Okay, so for any max or min, it's going to be defined there, so we're good there. We want to look at the derivative and what's the possibility for the derivative. So the derivative can be positive, negative, 0, or it doesn't exist. Okay, so those are the only possibilities. So we want to do like a case-by-case analysis. So we'll say case 1, it turns out that at this relative max or min, the derivative does not exist. Okay, so in this case, we have a relative max. So f is defined. And f prime of c does not exist. Okay. If f prime of c does not exist, it's automatically going to be a critical number. Okay. So that's what it just says. So if f is not differentiable at c, then c is a critical number. So case 1, it's automatic. Okay. Case 2. Let's suppose that the derivative is greater than 0. Okay. So case 2. We're kind of thinking, suppose f prime of c exists, then f prime of c is all these other cases. It's greater than 0, or it's less than 0, or it's equal to 0. Okay. Right. So let's suppose it's greater than 0. Right? Okay, what does that mean with regards to the limit definition of the derivative? So we note that f prime of c can be rewritten as the limit as x goes to c with this alternate form of the derivative, f of x minus f of c, like I was using above, all over x minus c. And then this thing will end up being greater than 0. And then if you look at this thing as a function unto itself, this statement is saying that the graph of this thing ends up above the x-axis. So the limit as x goes to this c value will end up above the x-axis at some number L up here, right? Okay, so from the definition of a limit then, I can find an interval around c such that for any interval I want around L, so I'm talking about the delta epsilon stuff, I can literally kind of bound this thing here, this difference quotient, away from 0. In other words, I can find a nice interval around c such that for any x I want in that interval, the output will be greater than 0. Okay. Because of this limit thingamajig that's going on. Okay. So we could extract that part of it and just say for, I don't know, some delta greater than 0, it will be the case that for all x within delta of c, this f of x minus f of c all over x minus c will be greater than 0. Okay. Okay, so if you're willing to accept that, then we can work with some inequalities. All right, so there's basically so how do we do this? Sorry. There's points on either side of C, right? So suppose then there's kind of two cases here. Suppose x minus c is so suppose x is to the left of c, so this will be less than 0. That will imply that f of x minus f of c has to be less than 0, because this quotient is positive. If the bottom is negative, the numerator also has to be negative. Okay? And if you solve that inequality, you'll see that f of x will be less than f of c. Okay? And we're saying that f of c is a relative extrema, so in this case we think it's a max, right? So if we suppose that x minus c is less than 0, okay, so now next suppose that x minus c is actually greater than 0. Okay, this then forces f of x minus f of c to be greater than 0, because a positive over positive has to be positive. And then that implies that f of x doctor appointment. Yeah, so x minus c is greater than 0 implies f of x minus f of c is greater than 0. F of x is then supposed to be greater than f of c. Okay, so what did we say? We said f of c is relative extrema. These two suppositions, though, are contradicting that. Okay. The problem is that to the left of our c value, if you're picking points over here, it's all of those corresponding f of x values will be less than this extreme value, which implies that f of c must be a max. Okay, this is implying that f of c is a max. But then when you go on the other side of c, you get this other supposition, which is implying that f of c is actually min. Okay? So you can't have them both. These two facts together kind of force a contradiction. Okay? These two guys together are a contradiction. So again, let's think about where we are here. We are given that f of c is a relative extrema. F prime of c exists, and so therefore f prime of c has to be greater than 0, less than 0, or equal to 0. So we supposed it was greater than 0, but if you do that, then on the left it seems there's no way for it to work, right? I mean, coming in on this direction, it's below, and then it hits here, and then it goes kind of above. That's what this is saying. The first supposition is kind of saying this side of it is below, and the second supposition is saying the other side is above. There's no way that this thing could be a max or a min if you've supposed that the derivative is greater than 0. Okay. There is no way we have a max or a min. Okay, that's what we suppose, though. Okay, if you suppose there is a max or a min there, it won't work. If you suppose there is a max or a min, and you're supposing, so if f is a max min plus f prime of c, sorry, if f of c is a max min plus f prime of c is greater than 0, this doesn't work. Does not work. Does not. Okay, I hope you're getting the picture. Okay, you could do the same baloney with presuming that the f prime of c is less than 0. You can kind of go through the same argument for f prime of c being less than 0. So if you suppose that f of c is max or min, and then you add together this fact that f prime of c, you suppose this is less than 0, that will not work either. Okay, so neither one of these will work. So the only way you can have a derivative being working, okay, so the only way you can have the only way to make it work in other words, f of c is a max min, and f prime of c exists, is when the only way to make this work is when f prime of c is equal to 0. Okay, and that turns out to be that will then imply that it's a critical number, because those are the only two possibilities for critical numbers. So if f is defined and f prime of c is equal to 0, then it's a critical number. Okay, so hopefully that wasn't too crazy. I really enjoy proofs. I don't know if I'm enjoying them, but they were a huge stumbling block in my career as a math person, quote unquote career, right? Basically, you know, if I did not figure out a proof, I would not be able to sleep at night, because you had to get these proofs done by the morning, and if you didn't get the proofs done, basically you were going to end up losing your scholarship and you'd be out on the streets, which is what eventually happened to me. So, I mean, I wasn't out on my streets, but I had to go live with my mom, you know. But yeah, and the deal is, this kind of thinking, at least 20 years ago, they didn't think like a computer could do this. You know, it's like a long time ago, they thought there was no way a computer could beat a person at chess. You know, this is like an art form. A computer can never figure that out. And then of course the computer figures it out, and it always moves along like that. So you know, in my wishes that I could go to sleep at night, I wished that there would be a computer that could do proofs. And that's kind of an active area of research. If you go on the Quantum magazine and stuff like that, they'll talk about computers that do proofs and things like that. And generally, when you do a proof, it's kind of heavily wordy. You know, you read proofs in the book, and there's a lot of words there. If I could do my math life over, I'd probably just sit around reading proofs in math books to get a hang of it, so I'd be good at it once I got to grad school, and I'd be able to sleep then. But yeah, so I kind of, at this point, think of proofs as like a bunch of little boxes. You know, there's facts that are floating around, and you got to connect them together into chains. And then the chains lead in one direction or another, and you're trying to force the chains to lead in a direction that you want, without making up little boxes that don't necessarily have any truth to them. You know, so I don't know. Anyways, you're going to be doing more proofs. I just want to warn you, we need to do more proofs as you go into more and more math. That's where the real bread and butter is. Okay, so there's that. So ultimately, what have we done? If f has a relative min or max at x equals c, then f prime of c either does not exist or it equals 0. Long story short. Okay. Okay, so what you'll be doing then in the homework exercises in the beginning is just finding critical numbers. Okay, so for example, let's pick out an easy one, right? So usually the polynomial type problems are real easy. Let's look and see if we can find one like that. All right, so used to be number 11, but okay, so f of x equals x cubed minus 3x squared. Okay, so what you do is take the derivative, and you get 3x squared minus 6x, and then you set it equal to 0. So I have 3x squared minus 6x. I'm going to factor out the 3x, so I'll have x minus 2. And then set each part equal to 0. So minus 2, 0. And then solve. And that is your critical numbers, very simply. But literally, you have to check if the places where the derivative does not exist. But in this case, that's not an option here. Okay, in this case, the only critical numbers will be where the thing is equal to 0. Okay, so usually when I do this, I'll say, all right, where is f prime of x? Where does that not exist? Okay, and in this case, it never happens. And then I'll look for where f prime of x equals 0. Okay, and in this case, we get x is 0, and then x is 2. Okay, so those are the critical numbers, 0 and 2. Let's look at another guy. So example, let's say f of x equals 4x all over x squared let's plus 1. Okay, so f prime of x will be low d high minus high d low all over the low squared. So it'll be 4x squared plus 4 minus 8x squared all over x squared plus 1 squared. And then we can simplify, so I have negative 8x squared plus 4 all over x squared plus 1 squared. And again, you're looking for critical numbers. So you want to know where are the places that f prime of x does not exist. And in this case, you could just set the denominator equal to 0. And that's never equal to 0, right? Take square root of both sides. Okay. In the real numbers, that never happens. So never. And then you look for where f prime of x is equal to 0, and basically just take the numerator and set it equal to 0, usually. So this will be negative 8x squared equals negative 4. Divide both sides by negative 8, so you get 1/2. And then x will be plus or minus square root of 1/2. Okay, and those will be your critical numbers. Let's look at a mildly harder one. So we have f of t equals t times the square root of 4 minus t, and t is less than 3. Okay, so f prime of t is going to be leave t alone, and then power rule, and then chain rule, plus take the derivative of t, it's just 1, so 4 minus t 1/2. I'm going to get a common denominator to make my life easier. So one of the reasons, again, why you want to simplify is for these kind of problems, because you're going to be setting them equal to 0 and solving them. So this will be 4 minus t to the 1/2 plus 4 minus t to the 1/2. Hoping I didn't make any mistakes. Common denominator, negative t plus, I'm going to multiply bottom and top by 2 times 4 minus t to the 1/2. 2 times 4 minus t to the 1/2. And then this will become, this times this is just 4 minus t, and then times the 2. And then this will be negative t plus 8 minus 2t, 2 times 4 minus t to the 1/2. Oh, geez. And then this is negative 3t plus 8 all over 2 times 4 minus t to the 1/2. Okay, so again, where does f prime of x not exist. And that's where the denominator is equal to 0, or even any negative under the square root. So there's those two issues. First, I have to make sure that this thing is not equal to 0. Square both sides, divide by 4, and with 4 minus t is 0, and then you end up with t is 4. But that's not in our domain because they only want values less than 3, so we can toss that in the trash. Then you need to make sure that 4 minus t is greater than 0. We just checked equal to 0. Usually it'd be greater than or equal to 0 for square roots. So we just have to make sure that t is less than 4. Okay. Otherwise, it won't work. The derivative won't work. And of course, just from the domain, I mean, the function isn't even defined there, so it wouldn't be a critical number anyways. Okay, so then I'm looking for where f prime of x is equal to 0. And for that, you just take the numerator and set it equal to 0. So I'll have 8 is 3t. In other words, t is 8/3. And that looks like our only critical number in that crazy scenario. Okay. Okay, let's look at maybe a trig version of this phenomena. Example, sine squared x, so it's f of x equals sine squared x plus cosine x, and we're on the interval from 0 to 2 pi. Okay, so I need the derivative f prime of x is going to be 2 sine x times cosine x. So that's power rule, then chain rule, minus sine x. Okay. So again, I need to find where f prime of x does not exist. And that never happens for us here. Where does f prime of x equal 0? So that will just be 2 sine x cosine x minus sine x equals 0, and then solve this trigonometric equation. So factor out the sine x. I get 2 cosine x minus 1. So where does sine x equal 0, and where does 2 cosine x minus 1 equal 0? So that the sine x of x equals 0 in the interval from 0 to 2 pi when x is equal to pi. And then solve the other guy, 2 cosine x is 1, so cosine x is 1/2. And then I'm thinking, where does that thing equal 1/2? Well, that's going to be at pi over 3, so that's one of my answers. And then 2 pi over 3, 3, 4, 5 pi over 3 in the fourth quadrant. Okay. I don't think we had one that had a critical number where the derivative is not defined yet. Let's look at one like that. Okay, so example, and these are easy to come by. You just take something like f of x equals x minus 2 to the 3 halves, or something like that. Is that going to work? Well, we'll say 1/2. Okay. Or, let's see if I got an example laying around. For some reason my brain isn't working this morning. Two-thirds. Okay, so f prime of x is going to be 2/3 times x minus 2 to the negative 2/3, which of course is 2 all over 3 times x minus 2 to the 2/3. Okay, so f prime of x does not exist. Where does that happen? Take the denominator and set it equal to 0. Okay, divide both sides by 3. Raise both sides to the 3 halves power. And then solve. So the derivative does not exist at x equals 2. That's one of the critical numbers. And the actual function does exist there. Then where does f prime of x equal 0? So in this case, it'll never be 0. You just multiply both sides by the denominator. So 3 times x minus 2 to the 2/3. 3 times x minus 2 to the 2/3. And you get 2 is 0, so no solutions. That'll never happen. So it never happens. And our only critical number then is x equals 2. Okay. Okay, back to this idea about closed intervals. We want to find basically the max and mins on these closed intervals. And they can happen at basically three different places, right? If you think of the critical numbers as 2 different places. But then so it happens at 2 places, the critical numbers and at the endpoints. So if you look at my first picture, there would be a critical number at x equals 0, but there wouldn't be a critical number at x equals 2, because unless the graph just dramatically goes downward, odds are it's going up like this. So this would not be normally a maximum. So if you're working on a closed interval, it's not enough just to look at the critical numbers. Okay, we're going to need to look at the endpoints as well. Okay, so again, the magic of the critical numbers is kind of leads us to where we think the max and mins are. Okay, but that might not necessarily always be the case, and especially if you're on a closed interval, it won't even give you the max and min all the time, right? So finding extreme values on a closed interval. And it's a little confusing. I know we haven't even been looking for extreme values yet. We've just been looking for the critical numbers. But the idea eventually is that the critical numbers lead you to the extreme values. Okay? And the only side note is that if you're on a closed interval, the max and mins may occur at places other than those critical values. Okay, they're not necessarily going to be critical values. It may be just at a max or at the endpoints, maybe at the endpoints. So you have to check the critical numbers. Well, I guess first find the critical numbers. Okay. And then secondly, you have to evaluate the function at first the critical numbers. Okay. And usually that gives you, that's the only place you're going to find maxes and mins. But when you're on a closed interval, you'll also have to check the endpoints. Okay. Okay, but that's really the only time. Otherwise, it's always just about critical numbers. Okay, so let's take a look at some examples. G of x is 2x squared minus 8x on the interval from 0 to 6. Okay, so I got to get the critical number, so I need the derivative. Okay, so where does g prime of x not exist? Well, that never happens because this derivative is just a linear function, so that's not going to be an issue. And then where does g prime of x equal 0? Okay, so 4x minus 8 equals 0. 4x equals 8, so x equals 2 is our critical number. Okay, so now we go back to the actual function because we want the height values, we want the y values, we want to know the min and the max. Okay, so we have to go back to this thing. So we're evaluating the actual function, and we want to do it at the critical numbers, so f of 2, but we also then want to look at the endpoints. And if we do that process, we'll get the max and mins. Okay. Okay, so if you plug in 2, you'll have 4 times 2 is 8, minus 8 times 2 is 16, so negative 8. If you plug in 0, you get 0. If you plug in 6, you'll get 72 minus 48, which will equal something like 24. Okay, and it's from these numbers we just identify the max and the min. So the min will be, there's a relative min at x equals 2 of negative 8. Relative max, or actually on this interval, I don't think we need to call them relative maxes and mins. There's always an issue. I think we could just call them maxes and mins. You don't need to qualify them or quantify them. So let's just say a min at x equals 2 of y equals negative 8, and then a max at x equals 6 of y equals 24. Okay. Let's look at another. H of s is 1 all over s minus 2, and we're worried about the interval from 0 to 1. Let's rewrite it to make it a little easier to differentiate. You can use the power rule. So h prime of s is negative s minus 2 to the negative 2, which I can write as negative 1 over s minus 2 squared. Then I need my critical numbers. So where does h prime of s does not exist? So set the denominator equal to 0. Yeah, looks like we get one critical number there. Well, that critical number isn't in the interval, so it's actually, no, we're not going to evaluate that thing. And then where does h prime of s equal 0? Well, never, right? If you multiply both sides by negative s minus 2 squared, you'll just get 1 equals 0, and in other words, it never works. Right, so the only points we have this time are just the endpoints. So we'll evaluate h of 0 and then h of 1. So h of 0 is going to be 1 over negative 2, which is negative 1/2. And then h of 1 is going to be just negative 1. Okay. So this guy here will be your max, and then this guy here will be your min. Okay. Okay, let's try one more. So we have f of x equals 2x minus 2x to the 2/3 on the interval from negative 1 to 3. So f prime of x will be 2 minus 2 times 2/3 x to the negative 1/3. Let's rewrite that. So it's 2 minus 4 all over 3 times x to the 1/3. So where does f prime of x not exist? Well, clearly it's where the denominator in the second term fails. So the derivative is 2 minus, it's this that becomes an issue for us, right? So we just have to make sure that's never equal to 0. And of course, the only place that'll be equal to 0 is when x equals 0. Okay, so that will be one critical number there. And then, is that in our interval? Yes, it is. So we'll have to evaluate that. And then where does f prime of x equal 0? So 2 minus 4 all over 3x to the 1/3 equals 0. So I'm going to multiply everything by 3x to the 1/3. I get 6x to the 1/3 minus 4 is 0. 6x to the 1/3 equals 4. So x to the 1/3 equals 2/3. So x equals the cube root of 2/3. Okay. Did I make a mistake there? Oh, I just copied the problem down wrong. I guess I'm okay. I'm just checking my work. Just 1 second, please. Well, seems fine. Okay, so we have apparently two critical numbers here. And so I'll have to evaluate the function at the endpoints and those critical numbers. So I'll have to look at f of 0, f of the cube root of 2/3, f of, I think it was -1, and then f of 3. At 0, it's 0. At -1, we'll have -2 minus 2 is -4. At 3, I'll have I don't know what, and my calculator, of course, is dead. What more fun? I'm going to use the crummy dollar store calculator. Okay, so let me try this. This is the last problem we're going to do. Okay, so 2 times 2/3 to the 1/3 minus 4 times, whoops, minus 2. 2 times, oh, crap, so that's wrong. I'm sorry. So 2 times 2/3 raised to the 1/3 minus 2 times 2/3 raised to the 2/9. This is freaking ridiculous. I got this little calculator. Oh my god. All right, hold on. Okay, sorry. So it's about, what did I get? Of course, now it's going to be a jerk about it. I just want the stupid... Oh, there it is. 1.13. 1.137. So 1.14. The second guy. 4. And then the last guy, if I put in 3, I'll have, create another one of these. 6 minus 2 times 3 to the 2/3 is about 1.8. Okay, I think. So the min is right here, and then it looks like the max is right here. Okay. Okay, so that's the idea. The overall picture, though, is we're going to be looking for maxes and mins. Basically, in all applications, a lot of applications, you want to find the maximum or the minimum. You want to minimize or something, right? Like profit or revenue or, you know, whatever. In that case, you'd want to maximize profit, obviously. So that's what we're going to be doing, and the first step is to find the critical numbers, and then the next section we'll have some theorems that allow us to determine if a critical number is actually a max or a min, relative max or relative min on an interval. Okay, so I think that's about it. Thanks for watching, and we will see you next time.